Hello wonderful person, this is Anton, and today we're going to discuss yet another bizarre discovery coming from the James Webb Space Telescope that once again might not make a lot of sense at first. And in this case, it's again an unusual galaxy containing something super strange inside, possibly representing some of the biggest stars we've seen anywhere. But as you might have learned from some of the previous videos, this is not the first time James Webb discovered something that's super bizarre and difficult to explain. And so let's talk about this new discovery coming from a galaxy referred to as JWST, the galaxy that you see right here, and talk about why this is unusual and what seems to be happening here. And I guess in this case, let's start with the galaxy itself. First of all, like previous discoveries, this is an AGN, active galactic nucleus. In other words, it's a galaxy that contains a relatively active black hole in the center that's then responsible for producing a lot of very powerful emissions visible from billions of light years away, which is of course the main reason we even found it. And it is pretty far away, redshift of 5.55, or essentially when the universe was only about 1 billion years old. So this is not the most distant galaxy, but it is pretty far away. And in this case we have two separate teams with two separate studies around the same time that both essentially confirm the same thing. First, there is a very active, very massive black hole in the center, and second, the chemical analysis of this galaxy does not actually make a lot of sense. And so in this galaxy there seem to be quite a lot of somewhat unusual observations. For example, the black hole itself has already been confirmed to be overmassive, as in it seems to be much larger and much more massive than expected for a galaxy of this size at this time. But the true mystery of JWST is really in the elemental composition and the ingredients inside the galaxy, because here the chemical signature is just bizarre and seems to be entirely different from a lot of galaxies we've seen around the same time. And right now, I guess just to give you a little bit of a spoiler, it seems to point at the existence of enormous stellar giants that up until recently have been purely hypothetical. But here we're talking about stars in tens of thousands or even hundreds of thousands of solar masses, basically representing the largest stars in the entire universe. And so let's talk about the evidence first and why researchers seem to think this might be the case. And so to understand why JWST is so unusual, we must first quickly look at how stars usually produce elements that eventually make up galaxies. So first, when astronomers talk about galaxies, they usually use the concept of metallicity. This refers to the abundance of elements heavier than hydrogen and helium, with a lot of these heavier elements like oxygen, carbon, and nitrogen basically being the product of stellar explosions or supernova. So if we have a lot of these carbons, oxygens, and nitrogens, it means that the galaxy has been enriched and the galaxy is no longer primordial and has very likely experienced several generations of stars. And while in the local modern universe, scientists established very specific relations that govern how these elements appear, with things like oxygen and nitrogen usually following slightly different timetables. For example, when it comes to oxygen, it's usually synthesized quite rapidly inside some of the largest stars. So here we're talking about stars heavier than 8 solar masses, with a lot of these stars eventually creating a type 2 supernova or the core collapse supernova that blasts all of this oxygen into the surrounding space. This is something that we even observe today all over the place. But nitrogen is a little bit different. It does take longer to produce and mostly comes from the internal fusion process within intermediate mass stars, usually between 2 and 8 solar masses. So it basically requires very specific conditions. And in this case, these types of stars release nitrogen much later in their lives, usually during a phase referred to as asymptotic giant branch star. And this always represents a late phase of evolution in certain stars, when they appear as very bright red giants with a very luminous and very large outer envelope. And though in this case the core usually consists of carbon and oxygen, this is when they also produce nitrogen. But nitrogen enrichment usually lags behind oxygen enrichment just because of the types of stars it's produced in. These stars are much smaller and usually live much longer, and so we actually expect a lot of nitrogen in galaxies that are more evolved. And so young, developing galaxies, especially those with relatively low metallicity, are also supposed to show low nitrogen to oxygen ratio. So we might see some oxygen, but we're probably going to see almost no nitrogen, which based on what we know about star formation and star evolution, sort of kind of makes sense. Or really I should say made sense until now, because the data from the near-infrared observations of this galaxy with the additional observations by the Very Large Telescope seem to show us the opposite. Here, scientists found that this galaxy exhibits an exceptionally enriched nitrogen abundance compared to oxygen. Specifically here, the so-called NO ratio, which was discovered by observing ultraviolet emissions coming from specific regions, seems to be approximately 20 times higher than the solar ratio, or basically what we see inside the Sun. And this incredible level of nitrogen enrichment puts this galaxy amongst the most extreme nitrogen-rich objects discovered at these distances to date, or technically even some of the most nitrogen-enriched objects for at least the first few billions of years in the existence of the universe. And so this actually creates a bit of a paradox. Given the overall low elemental content or metallicity, this galaxy seems to be a little bit too young and seems to be a little bit too underdeveloped. So it really should not have any nitrogen at all, at least using the normal process involving these intermediate mass AGB stars. So essentially stars that we usually see producing nitrogen. And so something here definitely doesn't add up. But things get even more complicated when we look at where this is located. Or basically when we look at how the chemicals are distributed with a process known as chemical stratification. And that's because this galaxy is not uniformly rich in nitrogen and seems to have very specific concentrations. And so here, by analyzing different wavelengths, scientists discovered that there seem to be two distinct regions. First one is the wider outer region. When observed using optical emission lines that usually trace gas that's a little bit less dense, scientists discovered that the galaxy shows subsolar nitrogen amounts, or basically it seems to be relatively normal. And so here the outer region currently makes a lot of sense. But the dense inner region is super strange. Here the central gas that was traced through the UV emissions, which also shows us much denser particles, seems to show us a lot of highly ionized gas, and that's where it seems to be also dramatically enriched in nitrogen. And so most of the extreme nitrogen overabundance is basically in the center, or very close to the center, because we don't actually think this is coming from the black hole. And this tells us that the enrichment was highly localized and very likely involved a central event, possibly inside some kind of a very dense region, with this enrichment not spreading to the bulk of the galaxy, but only happening in a very small area, possibly area that's just a few hundred light years across. And surprisingly in this area, compared to nitrogen, carbon is not enriched either. So basically both carbon and oxygen seem to be very similar to what we expect from a typical star-forming region, but nitrogen is dramatically enriched. And that means that atypical slow-acting stars or medium-sized AGB stars cannot explain any of this. They cannot explain why this region is so enriched in nitrogen, yet does not have as much carbon or oxygen. So what exactly happened then? Well, right now there is maybe one exotic solution. Here, the evidence from both of these studies and the overall conclusion is that this might involve the hypothetical concept referred to as SMS, supermassive stars. And these are hypothetical stars that are ridiculously massive and possibly similar to population 3 stars. We're not actually entirely sure if they're the same or not, and were very likely formed from pristine hydrogen and helium, representing the leftovers from the Big Bang. But because they lacked heavier elements, which usually limit how massive a star can get, these early conditions allow these stars to form into really massive objects far beyond the typical mass of about 150 solar masses. And so here the model suggests that supermassive stars potentially explain what we're observing. If they have a mass of anywhere from 1,000 to maybe 10,000 or even more solar masses, they would actually create these giant factories producing nitrogen, which would explain why we're seeing this. And so during the primary fusion phase, or the core helium burning, their massive turbulent interiors convert most of the carbon into nitrogen, which then is dispersed throughout the stellar envelope and escape through these very powerful stellar emissions. And critically, based on the models used in these two studies, the extreme nitrogen to oxygen ratio seems to simultaneously match the observations of relatively normal carbon, oxygen, and even neon ratios discovered inside this galaxy. In other words, based on the models, the actual chemical observations seem to match the predicted models. And if confirmed, it would make JS 3073 a crucial galaxy. It's basically a kind of a fossil with a chemical imprint left behind by some of the most massive stars we've ever seen. Now once again, we're not sure if this is population 3 stars, but they probably are, the first stars in the universe. And so if the discovery is one day confirmed, this has a lot of implications for cosmology, even when it comes to things like, for example, supermassive black holes. Specifically, the existence of supermassive black holes so early in the universe. If the black holes started from the collapse of stars, and they actually started from these supermassive stars, it would explain why we're seeing so many very massive black holes, as we've discussed in one of the previous videos, in extremely early universe. Because in this case, these supermassive stars, like those discovered in JWST 3073, provide an efficient alternative. A lot of these black holes can basically form from really massive stars collapsing into black holes, making something that's already tens or even hundreds of thousands of solar masses in mass after just a few million years. And even in this galaxy, where the black hole is possibly over 100 million solar masses in mass already, a very similar process could have taken place a few million years prior. Here, a supermassive star could have created a really massive central black hole, thus explaining the chemical anomaly, and of course explaining why this galaxy contains such a massive black hole in the center. The black hole that's once again overmassive compared to everything else. But, once again, because this is a brand new discovery, this is still just a hypothesis. For example, some of the previous propositions about these supermassive stars and population 3 stars suggested that they should form in pristine environments, basically environments containing pure hydrogen and pure helium, and not a galaxy like this one that's already kind of more or less mature. And so here it doesn't seem to match the environment perfectly, and we don't really expect primordial massive stars to exist in a similar galaxy. But then again, maybe these propositions about supermassive stars and primordial stars are just initially incorrect. As in, maybe they can form anywhere, and maybe that's exactly what's happening here. And so the fact that this galaxy is so enriched in nitrogen, and this has not been confirmed by two separate teams, is already enough evidence to suggest that something super bizarre is happening here, and most likely involving these extremely massive stars. Unless, of course, in some of the future studies, someone discovers a completely different method that seems to produce so much nitrogen all at once, which basically would suggest that the chemistry in the early universe was just kind of different. Maybe stars could produce these elements in some other way that they're just not able to do anymore. But there's really no evidence for any of this, so right now supermassive stars still represent the best explanation. And really the best piece of evidence we have here is the fact that this is all so localized and in such a small region. An extremely dense region close to the central black hole that possibly just contains some kind of a very small stellar nursery. And so here it just seems to involve very strange stars. And that means that we'll probably be discussing this object in some of the future videos once there's some additional updates, because at the moment that's really all we know. And so right now JWST 3073 provides a very important test bench for many different models of chemical evolution in the young universe, but also provides some of the best evidence we have for the existence of supermassive stars that might have served as early seeds for supermassive black holes. But in some of the future videos, we'll also discuss some additional discoveries of these so-called nitrogen-loud galaxies, or basically galaxies containing dramatically higher values of nitrogen, and talk about some of the potential explanations and what all of this means. Because right now, based on some of the previous observations in just the last year, they seem to be pretty common, which once again suggests that supermassive stars were pretty common as well. And so as scientists gather more data, and as more evidence and more confirmation becomes available, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying a Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.